Welcome aboard, guys. This is the beginning lecture of Pre-Algebra. So I've been teaching these courses, this coursework to kids around your age, roughly about like grade 6 or grade 5 or sometimes grade 4, and it worked, okay? This coursework does not just encompass just the basic stuff, but I'm introducing you to some, like more fundamental ideas, basically. So I want you to write down lots of notes that I'm gonna make down, and also like when you solve number 1 and 2, like all those practice questions, not the skill practice, but the practice questions that you see right under the, like page number 7 or page number 8 or 9 and so on. If you see these kind of questions, please write the notes, okay? Please write the notes and try to review most of the time, because I'm gonna introduce you to more ideas, okay? All right, so check this out. 1.1. What's 1.1? That's arithmetic addition, right? 1.1, we deal with addition property. So addition requires two things. Well, it doesn't require two things, but it requires two numbers to begin with. When we add two numbers, we get a number, right? That's something that we know. We say when we have a number added to a number, we get a number. Seemingly obvious identity, but this is not really obvious thing. In fact, if you add two, I guess like, odd numbers, you get even numbers. Well, adding odd and odd, it becomes even. It's not odd. So this is not something that is natural, but if you think about like a big picture, it's like, we have a box of numbers, and we pull out one number and we pull out the other number and we merge them together. And by merging them together, we can find exactly same number in that box. That's what it is. We call them closure property, okay? We call this closure property. I didn't write it down, so I want you to write it down. This is closure property. Closure property means that, well, it is closed under addition, meaning that if we add two numbers, we get the number. Not the number, but a number, okay? Okay, so now we're interested in the very property of this addition sign here. We call them binary operator. We call them binary operator because we need two numbers to begin with. Binary means two, okay? So check this out, What if we change order of addition? What if we change order? So does changing order matter? That's the question. Changing order, does that really matter? It doesn't matter. That's what it is. We call them commutative property. So what is a commutative property? Commutative property means that if I change the order of addition, in other words, like given two numbers, if I switch writing order in a way. So if I write the triangle first and the circle last, I guess, we get exactly same answer. That's what it is. And this is pretty important. This is important too. We sometimes call this abelian property. We call them abelian property. So there is a mathematician called Abel. I'm not sure whether he's a Swiss mathematician or a French mathematician, but there was a mathematician called Abel, and he was genius, of course. Now, there was a time that he had some kind of, a love fight, in a way, that, he went to a duel. Duel is like duel. What's duel? Duel means like fighting, right? It's fighting with guns, like pistols. So they fight to death. So he went to a duel, and right before he actually, went to a duel, he said, oh, maybe I might die, so maybe I have to compile all the things that I had done. So he compiled all the things, and those things that he compiled right before he died, and he died in early age. I think, if my memory is correct, it will be early 20s or late 19s or, late teens. He died in young age. He was prodigy. He was genius. And he went to a duel, and before he went to a duel, he compiled all those stuff. And compiling all those stuff, that became a treasure for mathematicians. Well, mathematicians haven't discovered, they haven't discovered lots of stuff until he actually compiled everything. So those compiled, worksheets and the papers that he wrote down was a very, it was literally like treasure to the world of mathematics. So yes, we commemorate this guy, Abel. We call him Abelian. But not so important, just the historical stuff, right? And there's another thing that you need to know. Commutative property requires two numbers, right? Requires two numbers. And we can flip the order, right? Flipping order, it just doesn't change the result. But the second property that we need to figure out is, in fact, this is something called associative property. And associative property and commutative property, they go together. They go along with one another. However, we need more than two numbers to deal with associative property. So we call them associative property. And check this out. Grouping order doesn't matter here. Now, here, order of computation doesn't matter. And in the bottom part, grouping order doesn't matter. In other words, if I compute this number first, well, that is going to be exactly same as computing the second, the third, or maybe I can group the first and the third together. First and the third together and compute them first. So whichever way we compute, we're going to get exactly the same answer. And this is really important, especially if you look at number 2. Wow, that's using this and also this. I think number 2 is using this. But anyway, let's look at the color box that I wrote down. I wrote down the commutative property and associative property. They are the basic ideas that you need to know. And the core idea is that the grouping order doesn't matter here and the flipping order doesn't matter. Okay, when we have this computation. Now look at this color box. Which of the followings are equal to 5 plus 61 plus 11 plus 19? And look at A, B, C, D, E. All of them are same. All of them are equal to one another. Why? Because flipping order doesn't matter and grouping order doesn't matter. So however we write them down, as long as they're all additions, they're all same. Okay? And how can a question be made? Look at number 2. That's what it is. But before solving number 2, I'm going to go on to number 1. Okay? Let's look at number 1. Check this out. Dan is a farmer who milks cows. Okay, so he got cows. His 100 cows line up in the barn and he begins milking them. Okay, the first cow gives 2 pints of milk. The next cow gives 3 pints of milk. The next gives 4 pints and so on, increasing by 1 pint each cow. Right? How many pints of milk does the 100th cow produce? Interesting question, right? Interesting question. We can compute them directly. And of course, I know that you guys can compute this directly too. But there's a fundamental idea that you need to know in order to solve this. This is something called one-to-one correspondence. Okay? So I'm just going to write 1-to-1 correspondence. So one-to-one correspondence means that a number is attached to the other number and so on. We're going to use this one-to-one correspondence in number 2, but also when we deal with number 1, we're gonna deduce some property or some kind of equation out of the whole sentences. That's basically using this one-to-one correspondence. Now look at this. The first cow. Look at the first cow. The first cow gives 2 pints of milk. 2 pints of milk. Yes? Look at the second cow. Ooh. The second cow gives 3 pints of milk. Look at the third cow. We give 4 not fourth, it's 4 pints of milk, and so on. So here's what's up. You can see the connection between 1 and 2, 2 and 3, and 3 and 4. They are 1-to-1 corresponding. We have a relationship. 1 is directly connected to 2. 2 is directly connected to 3. 3 is directly connected to 4, right? They are directly connected to each other. Now, this 2 is not equal to this 2 because this 2 talks about the pints of milk. We have different measurements, right? We have different units. So we're talking about different measures, and that is the number of cow, or I guess the position of cows. Like we line them up, and we're looking at the different positions of cow. Okay, so can you guess? This is something called induction, in fact. We're looking for patterns. We're looking for patterns, and it somehow we can say, oh, maybe the nth cow plus 1 is going to give me the milk. That's what it is. That's something called a linear equation. And this linear equation is the direct, I guess, a translation of the sentences that we've been seeing so far. So here's what's up. We're looking at 100th cow, right? We're looking at 100th cow and 101 pints of milk. 101 pints of milk. How did I know? Guess what? I put 100 down here, and I get milk. Or you could have deduced it in this manner. Well, look at the number of cows. Look at the cows. If I add 1, well, then I get the number of pints to the number of cows, right? So the position of cow actually directly determines the number of pints. So in other words, if I give you like the 17th cow, well, the number of pints is going to be 18 pints of milk. So we could have deduced anywhere, like any cow or any position of cow. So we've been using one-to-one correspondence and something called induction. Okay. Now let's look at number 2. Number 2, ooh. Put some stars, okay? Put a star. Not just one star, but multiple stars. I like this question. It makes us observe the question, or it makes us think. It's not just doing huge tons of bashing like, algebra. We're actually doing some kind of mathematical thinking here. Okay, and number 2 is, in that sense, is a really, really good question. So look at number 2. What is the sum of the first 40 positive odd integers? First, we have to know what odd integers are, right? What are odd integers? Odd integers are like 1, 3, and 5, and 7, and so on, right? They are odd integers, positive odd integers. What about even integers? It starts from 2, 4, 6, and so on. Of course, it can be 0. 0 goes inside the even integers, okay? 0 goes inside the even integers, but that being said, we're just looking at what? We're just looking at the top row. We're looking at the odd integers. By the way, this is a side note. I just thought about it. I'm being very like presumptuous. Like I'm not doing it like I'm not doing according to what I prepared. I'm doing actually more than what I prepare in this one. Now 2, 4, 6, and 1, 3, 5, 7. Well, they are even numbers, even integers, or we can call them 1, 2, 3, 4, 5, 6, like in this way. 1, 2, 3, 4, 5, 6, 7, 8. All those numbers as something called the set of natural numbers, right? We can call them the set of natural numbers. By the way, when I use pound, that means numbers, okay? So we have natural numbers. We can partition them into 2 parts. That's what it is. We can cut all the set of natural numbers into 2 sections. Right? The one part is even number. The other part is odd numbers. We call them partition. And we call them parity. Okay? We call them parity. So parity of natural number means that, oh, we're dealing with even numbers. Oh, we're dealing with odd numbers, and so on. Okay? So that's just the vocab, the side notes. And now we're going to look at the situation here. So I have to first figure out the 40th odd integers, right? 40th odd integers. What is 40th odd integers? 1 plus 3 plus 5 plus 7 plus 9 plus dot all the way to 40th. How on earth would we get 40th? Now, I don't want to write them down all because it's going to take a while, okay? So what do I have to do? Well, we're going to use the idea of one-to-one correspondence, okay? So this is what's happening here. Look at this. Look at 1. 1. That's the first number. This is the first number. Look at 3. That's the second number, right? That's the second number. Look at 5. That's the third number. Yes? And look at 7. That's the fourth number. Maybe we can find the relationship between the two positions, right? Maybe we can find, let's consider this like cow, the first cow. And that's the number of pints of milk, right? Same goes for the second cow, 3 pints of milk. Maybe we can find out the relationship, and maybe I can come up with the 40th odd number. That's what it is. That's what we want to do. So 1 and 2 are connected, okay? So how do we make this relationship? So can you notice that we're simply adding by 2? Can you notice this? Can you also notice that this is going to be 1 plus 2? This third number is going to be 1 plus 2 plus 2. And so on. Okay, what about this one? Fourth number. It's going to be 1 plus 2 plus 2, 2 plus 2 plus 2, which is 3. Or maybe we can use this different idea. Maybe we can say, oh, isn't that just 2 times 2 minus 1? Isn't this just 2 times 3 minus 1? Isn't this 2 times 4 minus 1? Right? That can be 2 times 2 minus 1. Or maybe we can say a 2 times 3 minus 1. Maybe this can be 2 times 4 minus 1. And I argued they are exactly same idea. And I'm arguing that they're same idea. Why? Check this out. Look at this. This fourth. That 4 comes down there. Okay? That 3 comes down here. But look at this 2. And look at this 3. As you can see, those 2 and those 3 are 1 less than the number of cows. So maybe I could have done, maybe I could have written it like this. And by the way, I haven't taught you this yet, but if you simplify this, you're going to get that expression. But let's choose the second line of thought, okay? Because it gives me the number of pints, I guess, the number of pints of milk according to the number of cows, or according to the numbers, right? The position of numbers and the exact odd numbers that we want. So, the 40th odd number, because the second number was 2 times 2 minus 1, and the third number was 2 times 3 minus 1, the fourth number was 2 times 4 minus 1, well, I could have made 40th odd number as 2 times 40 minus 1, which is 79. Yes? It's gonna be 79. All right? So, the whole thing turns into ... all the way. Look at this. That's 79. So 75 plus 75 plus 77 plus 79. Yes? Now, this is where we're using the properties of the addition. I said adding numbers, order doesn't matter, and how we group them doesn't really matter. Yes? Check this out. In fact, we can group the first and the last. We can group the first and the last number together, which is going to be what? 1 plus 79, that's 80. Yes? But what about 3 plus 77? What about 3 plus 77? We can group this in any order that we want, and I'm giving you this simple patterns. If you're grouping these numbers from the, from the outermost part into the innermost part, it comes out in a very funny way. Because the sum of 3 and 77 is going to be 80. And 5 and 75 is going to result in 80, right? Wow. So that gives me what? That gives me a lot of numbers that we want to compute, like easier way to compute, other than just 1 plus 3, that's 4. 4 plus 5, that's 13. No, 4 plus 9, that's 9. 9 plus 7, that's like 16. Like, instead of doing all those processes in this order from left to right, we could have done, because they're all additions, we could have done grouping, okay? And how many groups are there? Well, check this out. We have 40 numbers to begin with, right? We have 40 numbers to begin with. And how many bundles did I create? Well, I grouped 2 numbers together. So 2 numbers become a pair, right? So because 2 numbers become a pair, well, I'm going to have 20 bundles, right? So I'm going to have 20 bundles of 80. And I'm adding them up, which is going to be 80 plus 80 plus 80 plus ... plus 80. This is going to be 80 times 20. How many 80s do you see? 20 of them. So that must be 1600. So the answer is 1600. Okay, now we're going to move on to the next page, finally, arithmetic of multiplication. So we're going to deal with arithmetic of multiplication in this lecture. Then I will move on to, I guess we have time to cover up to number 4. And starting from number 5, we're going to do it from the next lecture, okay? All right, so check this out. Arithmetic of multiplication. Does it really matter? Yes, it matters. It really matters. This matters. So we're going to look at the multiplication sign first, okay? So by multiplying 2 numbers together, we simplify. We simplify lots of calculations. Like if we have same number of, suppose we have same numbers added together, instead of writing them all, usually what we do is that we come up with a multiplication sign, right? How many circles do you find here? There's going to be 3 circles. So because we have 3 circles, we call it 3 times this number. So it simplifies, it makes it more efficient. However, other than this just basic idea of multiplication, I just want to see the algebraic property of multiplication. Does order matter? Does order matter? Order does not matter. So pretty much same. Much same. Pretty much the same as the addition, okay? However, I just want to clear up some kind of vocabs. Check this out. If I multiply 2 numbers, I can call it with a dot. That's a dot. Okay, that's a central dot, in fact. It's in the center. Okay, we sometimes abbreviate multiplication sign by just creating a dot. And, well, what we're saying is that the order doesn't matter, so because order doesn't matter how we compute them first, given 2 numbers. Okay. But what about the grouping orders then? Grouping order doesn't matter as well. Grouping order does not matter. So that's commutative property. That's abelian. Commutative. But what about the abelian? Well, what about the associative? This doesn't matter too. However we group them, we get an expression like this. That's an associative property. This is an associative property. Okay. All right, so pretty much the same idea. And there's one last thing that we have to know. The one last thing that we have to know is something called a distributive property. Distributive property requires two things, two operators at the same time. We need multiplication and we need addition. Okay. So I'm just going to write distributive property. And by the way, I wrote down distributive property in my lecture notes, okay? In my notes. So if you look at the textbook, yes, you can find it. And I want you to write it down right next to it, okay? Distributive property requires this step. It literally distributes the multiplication. Order matters here. What order? The way you write matters. So, in your previous grade, or in your previous, I guess, learning, you would have heard the vocab something called PEMDAS. Parentheses, exponentials, multiplications, divisions, addition, and subtraction. That's what it is, like PEMDAS. We do things inside the parentheses. We compute, we perform arithmetic inside the parentheses. That's the first thing that we do. However, if we have a multiplication sign, we can actually distribute this separately, okay? So that matters too, that matters too. Okay, so distributive property requires two operators, again, two operators, right? Two operators, and we don't have to follow the PEMDAS, okay? We're not following the PEMDAS in this case because it can get distributed. Sometimes this is better. Sometimes this is way easier, okay? Now look at the example that I wrote down here, the color box. We use both commutative and associative property. Now this makes it really simple. In other words, if I give you an example, something like 2 times 3 times 25 times what? 5 times 4 times 10, guess what? We could have done from left to right, right? We could have done from left to right. That's kind of hard. That's difficult. That's challenging. Maybe we can make some calculation error, okay? But the idea is that if you look at the answer, it's really simple, right? 30,000. It's 30,000. So how do we get 30,000? This is how we get. Look at the numbers, 2 and 5. If you multiply 2 and 5, that becomes 10, and 10 is a good number. Why is that a good number? Well, because when we write 10, we just don't have to write down the units digit. It's just 0, right? So circle 2 and 5. That becomes what? That becomes 10. Look at 25 and 4. If you look at 25 and 4, if you multiply these two numbers together, we get what? We get 100. And also, there's 10. So 3 times 10 times 100 times 10 is going to be 30,000. Of course, we would have gotten the same answer if we computed from left to right. Exactly same answer, okay? Exactly same answer, but this, you know, simplifies our life. It makes it more efficient. Okay, so that being said, I want to look at number 3. Okay, look at number 3. What is the product of all non-negative one-digit and we need to figure out what non-negatives are, right? Now we know what integers are. You guys know what integers are. It's pretty. It's larger than, it's more, I guess, it has more list of numbers than the set of natural numbers because it's signed natural numbers. Now, think about integers. I'm just going to write it integers in this manner, okay? Integers starts from, well, we can make it start from 0, okay? It starts from 0. And look at 1. It can be positive 1, it can be negative 1. It's going to be positive or negative 1. Think about like 2, positive or negative 2, and so on, positive, and so on. We have signed natural numbers. I call them signed. It has signed. signed natural numbers. Okay? So, we have an integers. However, if you look at this, non-negatives. What is non-negatives? So we need to distinguish integers into three parts. We need to distinguish integers into three parts. I want you to write this down, okay? We can call positive integer. We can have a positive integer. Or we can have negative integer. And also, what about zero? What about zero? Zero will not have any sign attached. Look at this. It doesn't have any sign. It eats every sign. When positive comes in, zero eats it away. If negative sign goes in, it eats it away. It's just gone. It gets digested. There's no sign attached to negatives. Okay? Okay. So what about non-negatives then? What about non-negatives? Non-negatives are going to be these numbers. They are non-negatives. Okay, so check this out. We multiply unit digit, one digit integer, starting from where? 0, 1, 2, all the way to 9. But look at this. That's horrible. This is horrible, but we have 0 in front, and 0 eats it away, every single thing. It becomes 0. What? This is what it is. 0 times a number becomes 0. Okay, let's look at number 4 and be done. Okay, number 4 is pretty simple. Read the question as I erase this. Okay, read the question, please. So check this out. 10 pictures, each measuring 4 inches by 6 inches, are mounted on a piece of green poster. Okay, there's no overlap, so each of the figure or each of the picture has its own area like attached or intact. It's safe, okay? The poster board measures 20 by 17 inches. All the shapes are rectangular. Okay, all the shapes are rectangular. How many square inches of the green backboard will show after the pictures are mounted? What's the key idea that we need to remember? The key idea is something called complementary thinking. So what's complementary thinking? We evaluate or we calculate the whole thing and we subtract those things that don't work, that don't fit. What's the whole thing? The whole thing is what? 20 times 17 minus. What are the things that we need to subtract? 4 times 6. Each picture measures 4 times 6. Times how many of them? There are 10, right? 10. Ooh, so what are these? That's 240. How did I know? Really fast. Well, you can compute this number first. That's 24. And if you multiply by 10, it becomes 240. But what about this? It's 340. If you subtract 340 by 240, we get 100. So 100 units. What are the 100 units? Units are going to be inch square, square inches. And that's it. That's it up to number 4. Well done. Well done listening up, listening up to this long lecture. I want you to repeat though. Okay, I want you to repeat though. Then next time we're going to start from number 5. All right, I'll see you next time. Thank you.